Hey there, in this video we're going to talk about the inverse hyperbolic trig functions and also about the mean value theorem for integrals. And so here's a table of, just to recall from earlier in the semester, the table of derivatives for your inverse hyperbolic trig functions. And remember the regular trig, hyperbolic trig. So regular, hyperbolic. We had the sinh of x and the derivative is cosh. And if you had cosh of x, the derivative of cosh is sinh. So these are the ones where we don't have the negatives for in standard trig functions, right? The derivative of cosine is negative sine. But here, the derivative of hyperbolic cosine is just positive hyperbolic sine. And then the hyperbolic tangent, the derivative is hyperbolic secant square. So very similar, and then we can go down the line with the other ones. So what this means is then that if I had, if I wanted to integrate, say I want to integrate the sinh x times cosh to the fourth of x dx, how would I integrate that? This looks like a u substitution problem where you want to ask yourself, does the derivative of one part equal another part of the problem? If you can't do it just by looking at it, which as soon as you see a function, especially a trig function to a power that is not a square, then we probably can't do it just by looking at it. So we want to make a u substitution. So let u in this case be cosh of x, because the derivative of cosh is sinh. Remember, I don't want to have my du trapped in any sort of power. So for example, so this is my warning here. If I let u be sinh of x, right, my du is cosh. So some of us might think like, oh, I can let u be sinh because cosh is the derivative. But then when I do the integral, right, this will look like u times du to the fourth. And we can't have that, right? And it actually wouldn't quite work out that way because du is cosh x dx. And this is just cosh x to the fourth, so we wouldn't really be able to make that substitution. But my point here is that we do not want our du trapped inside a parentheses or in the denominator or something, or as a power. You want to be able to write the new function, whatever your transformation is. If you go from f of x to then a g of u times du, you want to be able to have your du off to the side. So that's why I'm letting u be cosh, because that's the thing to the power, and the derivative of cosh is sinh x. Don't forget the dx. So what is the new integral? The new integral becomes then, let's see, our sinh x dx is du. So I'm going to have cosh to the fourth. So that is u to the fourth. And then sinh dx is du. And now this is something that I can do just by looking at it. This is the general power rule. So then I go, this is u to the fifth over 5 plus c. This is indefinite integral, so I need the plus c. And then substitute back what u was. U was cosh. So hyperbolic cosine to the fifth of x over 5 plus c. So that will be our final answer. So this is when I have regular hyperbolic trig. Now with inverse hyperbolic trig, we want to be able to, so these are the derivatives. So this is, recall, this is from earlier in the semester, section 3.11. These are the derivatives. So now going backwards, what this will mean is that if I have the integral of any of these, right, I'm going to get this function plus a constant. So let's explore some other examples. So in this next example, we have the integral of 2 over 1 plus x squared dx. And so first thing is, can you do it just by looking at it? And is it a basic antiderivative? And yeah, this one is actually not too bad. This is, if you can take the 2 out, and you have 1 over 1 plus x squared. And hopefully you recognize that as inverse tangent. So this becomes 2 inverse tangent of x plus c. Or you can write it as 2 arctan with the alternate notation of x plus c. So that will be the other way. So that one is not too bad, right? So this is what I mean by, can you do it just by looking at it, by recognizing that this function is the derivative of inverse tangent, right? This function is the derivative of something that we know. Now what about example C? Now this example, when I look at it, I don't quite recognize. It looks kind of like that one, but it's a little different. So let's look at the inverse. Notice that, which one is it here? The 1 over 1 minus x squared is the derivative of hyperbolic inverse tangent. So I can then look at this and say, oh, this is actually something that I do know how to do. This is the hyperbolic inverse tangent of x plus c. But this means that you have to memorize or know to identify your inverse hyperbolic functions, right? When you have now notice that for inverse hyperbolic inverse tangent and hyperbolic inverse cotangent, they appear to be the same. And so recognizing these derivatives as these are the derivatives of hyperbolic inverse trig functions can really shorten some of the work. So for example, in part C, when you are in Calc 2, you will be asked to solve this using a method that is called partial fractions. That is the other method that this can be solved, which is a very lengthy method. But knowing that this is the derivative of a hyperbolic function, inverse function, can shorten all of this work. This is a pretty involved process of doing partial fraction decomposition to be able to solve this integral, and in the end you end up getting the same answer. So knowing your hyperbolic inverse derivatives forwards and backwards is going to become really, really helpful in Calc 2. Now for example D and E, I want to look at them at the same time. So can you do them just by looking at it? And for D, yes, right? Notice that that is the 1 over the square root of 1 minus x squared is the derivative of inverse sine. So that means that this is going to be just inverse sine of x plus c. So knowing our derivatives forwards and backwards is really helpful, right? So here I can say, oh, that's just the derivative of inverse sine. So that means that the antiderivative is inverse sine plus a constant. So that's how we can do it by looking at it. Now this one is 1 over the square root of 1 plus x squared, so it's no longer inverse sine. And when you get to Calc 2, so in Calc 2, this is going to be another one that's going to be a lot of work. You learn the method of trig substitution, which is a very interesting method. It's fun, but fun for me, so that usually means a little bit of work and frustration for students. So, but notice that if you know your hyperbolic inverse functions, where do we see that? 1 over the square root of 1 plus x squared is actually the derivative of hyperbolic inverse sine. So then that means that I don't have to do all that work that you'll learn in Calc 2 to solve this problem using the method of trig substitution, because I can bypass that method and say this is hyperbolic inverse sine plus c. Now if you had limits of integrations here and you plug them in here, you will get the same answer as if you go through the full method of trig substitution and then plug the values in. Right, because it's the same function, you're finding the same area. It's just that knowing your hyperbolic inverse derivatives really will simplify this crazy work. When you get to Calc 2, trig substitution is going to be one of those methods that makes people scratch their heads a lot. Not in a bad way, it's just, just warning you about some of those methods. like the method up here, partial fractions can be very time consuming. So for some, right, when you see these inverse hyperbolic inverse tangent and inverse cotangent, those might be good ones to know so that you can bypass all that work in Calc 2 for that particular integral. And the same thing here for inverse hyperbolic inverse sine and hyperbolic inverse cosine, and even these do. Oftentimes they require trigonometric substitution, but if you know that these are the derivatives of hyperbolic inverse functions, then you can save yourself a lot of work. All right, so now we're going to go into the mean value theorem for integrals. Oh wait, I have one more example. Never mind. I almost forgot to do this example. So the last one on this, I wanted to be able to do a use substitution. Right, because when you look at this, can you do it just by looking at it? No. So that's the derivative of one part equal another part of the problem. My first instinct is to say no, but I see that I have an x there, and x is the derivative of x squared. So I know I can write the x to the fourth as x squared squared. So I'm going to rewrite this as the integral of 6x over the square root of 1 plus x squared squared. And we've done this before in a prior video. And so now I can say, oh, now I can let u be x squared because du is 2x dx. Do I have a 2x dx in my integral? Yes, right. In fact, 6x can be written as 3 times 2x. And so you have 2x dx is our du. So then we can rewrite the new integral as the integral of 3 du, because 2x dx is du, over the square root of 1 plus u squared. And now we can take that constant out and say du over the square root of 1 plus u squared. And this looks like the one that we just did, 1 over 1 plus x squared square root. So that is the hyperbolic inverse sine. So this will be 3 hyperbolic inverse sine of x plus a constant. So that will be our final answer for that one. All right, so lastly, now we can talk about the mean value theorem for integrals. And we had a mean value theorem in general that essentially told us we could find the average value of the average y value of a function. So here, the mean value theorem for integrals is essentially tells us that the integral from a to b, we can find the average area. There's a value that essentially splits the area into the average. So let me illustrate that with a picture. Essentially what that is saying is that if you have the area, right, from a to b under a curve, so this blue shaded area here, then there is at some point between a and b, there's a value of c, so that if you do the area of that rectangle, right, that height, so f of c, the height of that rectangle, and then the length is the whole length of your interval a to b, that area of that rectangle is equal to the area under the curve. And so that is a pretty interesting result. And so the f of c becomes the average value. So that's essentially what we're saying, right? The f of c is the average value of the function. So let's try some examples. We want to find the average value of the function on the given interval. So we have f of x equals 4 sine x on 0 to pi. So essentially we want to find the value over here, right? We want to find the f of c. So where along our function do we get a function value that gives us the whole area? So that means that we're going to have f of c is equal to, and let's remember our formula for the average value then is 1 over b minus a times the integral from a to b of f of x dx. So we're going to have 1 over b minus a, so pi minus 0, times the integral from 0 to pi of our function, so of 4 sine x dx. And then we solved this integral. So f of c, the average value of the function, is 1 over pi times, and then let's integrate that. What is the integral of 4 sine x? You can take the 4 out, so you're really just looking at the integral of sine x, which is negative cosine x, right? You're taking the antiderivative from 0 to pi, and then evaluate this. So I'm going to have 1 over pi times, where happened to my 4? So minus 4. So it'll be negative 4 cosine of pi minus a negative 4 cosine of 0. And evaluate that. So I have 1 over pi times cosine of pi is negative 1. So I have negative 1 times negative 4, so that will be positive 4. Cosine of 0, that's 1. So I have negative 4 times 1 is negative 4, so minus a minus 4, so plus 4. So I end up with 8 over pi. So that will be the average value of the function. So 8 over pi will be the y value, where I will have to then draw the height of that. So 8 over pi times b minus a is going to give me the value of the area. And let's try part B. So same thing here, find the average value of the function. G of t is the ln of t over t on 1, 4. So that means that our average value, so f average is our f of c, right, for some c, is equal to 1 over b minus a, so 4 minus 1, times the integral from a to b, so from 1 to 4. Remember, when you see the interval like this, this is your interval a to b. So a is the lower limit, b is the upper limit. So 1 to 4 of ln of t over t dt. Can we do it just by looking at it? No. The previous one, the integral of sine, I could tell that that was negative cosine, but here I can't do it just by looking at it. But so then I ask myself, does the derivative of one part equal another part of the problem? Yes, the derivative of natural log of t is 1 over t. So that means I can make a u substitution. Let u be ln of t, because du is 1 over t dt. And so I can see that there's my dt over t, there's my dt over t, so that will be du. So now we can say, what is the new integral? So our f of c will be 1 over 3, right? 4 minus 1 is 3. And the integral of u du. And here again you have the option, I've done it in prior videos with u substitution. You can either leave it like this and integrate and put it back in terms of the original variable, or using your substitution you can change your limits of integration. That way you don't have to go back to the original variable. I'm going to not put my limits of integration, and I'm going to go back to the original variable. So, right, the thing that I want to make sure you understand, right, these are t, my variable is t here, so these are t values. T equals 1, t equals 4. So I don't want to put 1 and 4 here, because these are t values. T equals 1, t equals 4, and now I have u's. So we can't do that. So I'm just going to leave them blank. So don't make that mistake. And I'm going to integrate. So this will be 1/3 u squared over 2. So my final will be 1/6 u squared. And now go back to t's, back to the original variable. In this case is t. So this is going to be 1/3, 1/6. And then u squared. What was u? Let's look at our substitution. U was natural log of t. So then this will be 1/6 ln of t squared. And we're evaluating this now from 1 to 4. Now I put my original limits of integration back, because I'm back to the original variable t. So I can put those t values in. And so evaluate. So I'll have 1/6 times the natural log of 4 squared minus 1/6 the natural log of 1 squared. But hopefully by now we know natural log of 1 is what? That's just 0. So that whole thing goes away. So we're just left with our final answer then for the average value of the function is 1/6 times the natural log of 4 square. Now be careful here, don't say like, oh, I can bring that exponent down by properties of logarithms, right? That's not how that works. Here the natural log is a thing that's being squared. If it was the natural log of 4 square, now I can bring that 2 to the front, right? But I can't bring that 2 because this means that the natural log itself is the thing that's being squared. So careful about mixing up your exponents. So that means that the area, right? So this will be the height. So if I make a rectangle of length 3, right, from 1 to 4, this is 3, and the height of this rectangle is this, that height, then the area, so 3 times this, is the same as the area of the integral here, right? The area from 1 to 4 of the function, the area under the curve and the x-axis, between the curve and the x-axis. I was trying to find the word between there. All right, so that's how you do the average value of a function. So essentially what it's telling you is that the average value is the y value along the function, that if you use that y value as the height with the length of the interval, that area of that rectangle created is the same as the area between the curve and the x-axis. And so that's average value. You may see it again in Calc 2, but it is something that is supposed to be covered in Math 400, so I just wanted to cover it real quick. This will not be on the final, but I just want you to be aware because it does come up on applications later on in Calc 2. All right, email me if you have any questions.